in about maybe give it just one more minute for anyone else that might be joining us. And I'm Anthony Will, and I'll be your guest speaker today in your leadership lecture series. I'm really honored to be here at Purdue to be a part of your program and a part of the program's objectives to give you some exposure to people who are in industry. I work for General Motors, and I think we've had a chance to be we've been a part of EPICS probably even since its inception, when I think it was Dr. Jameson started it. You guys probably know the history behind it better than I, but I go back at least 20 years, I think, with EPICS, and it may have a starting date of maybe 5 years prior to my memory of it exactly. So, but when you think of, at least when I think of the ideals of engineering in particular, you know, we're supposed to use science and mathematics and our deductive reasoning to develop products and things that are useful to people and to humanity. And for you to be a part of a program that is doing that in the community, I think is pretty phenomenal. I hope that you're getting a lot of satisfaction from the learning experiences as well. I hope you're getting satisfaction and also benefit from it. So it's kind of nice when those two can be partners. Not sure if we have someone else who's going to join us, but my goal today, and I hope you'll just permit me to do this, I'm going to stand here for about 50% of the time, and I'll probably move to the middle of this over here, but I'm going to walk back and forth because I don't have a pointing device, so I'm a remote one. I'll have to use my mouse here. And then every once in a while I have to take a break to defog my glasses because I've got to get used to speaking through the mask over a period of time, so I might not even be able to see a couple of my slides here. But just a little bit of background on myself. I'm a Purdue alum. I'm a graduate of the School of Electrical Engineering. I have a master's degree in electrical engineering, and I have a PhD in electrical engineering also from Purdue, classes of 91 and 97. So I did 2 tours of duty, is what I like to say, at Purdue University, and they were some of the most dynamic and exciting times in my life. You might be questioning how dynamic and exciting my life is if that was as dynamic and exciting as it's been, but no, it was actually fantastic. So I'm really happy to engage with you all today. So my talk today is going to be on the space that I'm working in right now, and it's automotive product development in using virtualization. And I know each of you are engaged in a lot of work where you're using, or schoolwork, and learnings where you've used virtual methods, where you're not building physical parts, you're actually maybe you have whatever the latest CAD package is out there. You might be designing a beam of some sort, and you're trying to optimize the weight of that beam to its strength. And you're not building those parts up one by one out of metal. You're not finished, but you're actually creating a part in a virtual sense, and you're giving it all of its physical parameters, and you're able to do amazing analysis and testing and studying. Well, let's take that just one step further. We've moved from doing parts to basically trying to integrate this into the entire vehicle development system and process. Most of my talk today is, although I'll be relating it back to what we do at General Motors, it applies across the industry. Industry is taking these steps right now towards virtualization. So that's the first part of my talk. And then the second part of my talk, I'm going to do a little bit of a pivot, and I'm going to talk to you a little about leadership and the type of leadership it takes to usher in technology like that, to make basically kind of like a step function change in how we go about doing work. And what I wanted to leave you with was something I hope is valuable to you, and it's about talent spotting in the 21st century. How are we identifying leadership talent in order to usher in this kind of change? And the reason I think it may be valuable is this. First of all of you are in the process of crafting your careers. You're here getting your education. You've got goals and dreams and aspirations ahead of you. And leadership is certainly going to, I'm pretty certain your ability to be a great leader or to have leadership attributes is going to be an important part of your future. So I'm going to talk to you a little bit about How do we go about identifying, how is industry going about identifying leaders? So that takes me to SOE. So I did a little introduction so far. I told you I didn't define virtualization, but that's my outline, defining virtualization, and I'll have my leadership message. But here, let me start with the first slide, and if it's okay, maybe I'll talk from here for a second, and I'll step out when it's necessary. So virtualization is creating a virtual representation of something that is physical, but it's not that actual version of that thing, right? Such representations allows us to take things that are physical systems and express them like in terms of their physical laws or mathematically describing them so that they can be observed, you can study them, you can analyze, you can manipulate them in ways that you can get insights about those systems. And it could be anything. In our case, they're electromechanical, chemical type systems, software controls. We're taking those to the virtual space. As you can see there's an engineer, and she's standing outside a representation of a vehicle that has like a battery pack at the bottom, and then you see the neon wireframe vehicle skin that's around it. You know, it's really not there, but through the apparatus that engineer is using, they're able to see spatially where these things kind of fit. So manufacturing uses virtualization. People who are developing products are using virtualization. Even the ideas of even gathering requirements sometimes utilize virtualization. So that leads me, I mentioned the word requirements. It leads me to my next slide, which is virtualization and development cycles. I take it that maybe in some of your engineering classes, have you guys seen this V cycle before, where it's like a development cycle? You might even see it if you studied agile kind of like systems in your engineering classes. But this V diagram doesn't mean virtual in this case, but the shape is kind of ubiquitous. It's throughout all design engineering. And if you start in the upper left-hand corner, think of it, it says operational concepts, that is, or concepts of operation, but it's basically the customer's voice. What the person who's going to buy your product, what are they clamoring? What are they asking for? Next step in that is we put together requirements based on that. You know, turning someone's wishes into hard numbers so you can do a design and develop a product. And as we kind of go down that V, after you got your requirements, you're able to build like an initial prototype. And once you build that initial prototype, you start taking action on it. You start exercising it and trying to understand where the design, if there's design flaws, you start testing that design. And you do that on several levels. You do it on a component level, you do it on what they call a subsystem level, several components together working as one. Then you take all the subsystems, you put those all together, and you start using it as a whole unit. And then you do something they call unit test, which is up in the far, where it says accepted testing, at the far right corner of the V, and that's where you validate your product at that point. Now, this is kind of as I said, it's kind of ubiquitous. It's the method in which most manufacturers, product developers use. I don't care if it's software, if it's automotive, if it's tractor equipment, software even. This is what we use. Now, you see the dollar signs kind of up there. That one didn't happen to be my slide, but the dollar signs make sense because that's kind of like opportunities where virtualization really kind of pays off. Instead of building hard parts and systems, we can use these methods of virtualization to improve our ability to be faster. This V cycle here, although it looks like a process, think from left to right as being time, because that's kind of how things happen in time. And the key thing here is how do you, if you notice the big arrows pointing over to the right, from right to left, that's where the opportunities are for improving getting to market fast. Developing a product and doing it very quickly, it really comes down to taking that V cycle that looks like this and kind of moving it like that, right? So you're trying to shrink your development time and do things more in parallel. All right, that kind of leads me to, next slide, just one moment. All right, so that's so hence it's kind of like, hey, why are you guys going virtual, General Motors? And I'm really kind of showing you the slide because like I said, it's where industry is going. they're doing so many different things. Our company is in partnerships with like Lockheed Martin, we show here. We're in partnerships with the photovoltaics companies like LG to build batteries. You know, we're engaged with Cruise and Microsoft, you name it. And in order to really engage at the levels in which we are, we have to be able to share information and data and test methods and all of that a lot faster in order to really take advantage of the time and scale of our organization and the audacious goals that we have. So just think, all industry has audacious goals for their development. And I'm going to show one of those now. Hi there. See, next slide that I have here, or at least as the slides are, the points are coming up here. This picture is of Mary Barra. She's our CEO of our company. I'm very proud to work for Mrs. Barra. But Mrs. Barra in 2018 put a big target out there for General Motors. She said, we're going to make a $6.5 billion reduction in our engineering and product development budget. And I mean, that's it's a staggering number. But the way in which we can achieve something like that was, first of all, we went for, prototype tooling is what it says there. So, you know, when you build prototypes, they can be really expensive, these one-off kind of products. And all the material that goes into all the steel that we buy and rubber, and you think of the kind of raw materials, they have fixed costs, and it's very expensive. And the cost can, when you're talking about building millions of things, it certainly becomes quite expensive. So one of the first opportunities to trim our budget was to trim our budgets in terms of this kind of like structural material costs. And how did we get there? You probably say, it's probably your topic, Mr. Will, it's probably virtualization, and your answer would be correct. That's how we're getting there. So we've got this company called BrightDrop that's kind of transforming the mobility industry for the delivery of products. Any of you all have seen our Hummer? We got this electric Hummer. It's really exciting product out there. Okay, I'm getting a few nods of heads there. I'm really happy that you've seen that. We're really excited that we were able to deliver something like that within like 2 years. It's really been, and virtualization has helped us to do that. But this slide here, it's not a slide to study, but a slide that I just want to show you a couple of things. The blue bars that you see up there is kind of like, we call that our development process, if you would, and it's like 4 years from like the start of a product to when it finally reaches our customers. But our CEO has challenged us to take 2 years out of that. You know, like take 2 years out of it in the next 3 years, so that you're able to be very agile with turning around the products. And the way in which we're going to get there is we've had to abandon some old ways of thinking and start to embrace more of our ability to do these things in math and to do them virtually. So this is how we're going to achieve it. So it doesn't mean there'll be no prototype tooling or what have you, but it's going to be less of those things. I'm going to just kind of skip through a little bit of the slide here, but what I wanted to point out with this one icon is that changing the hearts and minds of our people is another important aspect of kind of bringing on such a kind of a radical, if I'd call it radical, let's just say it's just a very step function change in how we've done business, the engineering business. Just one moment. So kind of like, why are we doing it now? You know, and you probably realize, you say, hey, you know what? It's a tough market out there. If you don't jump on board quickly and try and are able to use your speed and agility, you're going to be out of business. And General Motors knows that, and every other company does. Just because you've been around 100 years doesn't mean you'll be around 5 years from now. And that's what we have to use methods that some of the more recent, I should say, companies that have joined the mobility field, and they're doing very great in delivering products. We've got to be able to compete from a speed standpoint as well. But so, you know, industry's going in this direction. Why? We want to do a couple things. We want to reduce our hardware that we're using, because that's a cost. If we go faster, that means our customers get a product that they want sooner before your competitors necessarily get it there. Or, you know, we live in a time where I want my new phone. And people want their phones and their cars at about the same development cycle. So we've got a pretty big job in front of us. But speed, speed, speed. It's what makes the Purdue Boilermakers in every sport great, right? Or when they do it very well. It's about being tactical, and strategic, but also being able to do that at a very high speed. Another thing is that something they call built-in quality, and that comes out of a concept of kind of like total quality network, the Deming methods of continuous improvement of your product. And what virtualization allows us to do is this. Instead of building something and testing it and then understanding what kind of a quality product that we've got, we build it virtually and we test it frequently and we learn from it. So the advantage of doing things virtually is not that, I'll say the main virtue behind virtualization is that you get the chance to study and understand your product in ways that you can't study and understand it with just building physical parts one at a time. Ultimately, I keep coming back down to cost. That's kind of a bottom line issue, right? So remember, speed is a very important aspect to this. We've all seen the old tortoise and the hare. The thing is this, what we're really trying to, I guess, promote, and I'm trying to promote to you, is that it's important to be the hare that doesn't start sleeping at the beginning of the race. You want to go as fast as you can during the entire race. You got to run your race. And that's what we're using these methods to do, to help us to run faster and do more up front. Because the earlier you catch defects, and that's another one of Deming's main principles in his total quality philosophy, catching defects early allows you save money doing that. And when you catch defects or problems with your design, you fix them early on and you deliver a much better product at the end. So it's all about running fast. And the main thing is this: if you see that hand that says, hey, moving to the left, remember I talked to you about that V cycle? Well, that's what this moving to the left means, just left in time, making sure that you can not say compress time, but do as much as you can earlier with your product development. And you want to run at the speed of your design. I'm going to talk to you a little bit about built-in quality. So I mentioned that before. What is built-in quality? It means developing a product or service service that's done right from the very first time that you build it. Now, I'm going to juxtapose something here in just a moment. Imagine we got this vehicle sitting here, and I'm going to try to put an analogy together from a physically built vehicle versus one that's virtually built, and what are the characteristics of those two. So on the right, and what's being filled in on the screen right now, is inherently a physical system has a specific geometry, it has specific material properties, it's got some specific physics. But if you want to know more about it, you actually, when it says you have to ask it, that's kind of an interesting concept. But you have to probe into it to understand what are the properties of that system. If you have a virtual system, for instance, you have defined, first of all, what the geometry is. You've had to have a clear understanding of what material properties are there, because they go into your representation of it. The physics are understood. You have to know many things up front. You don't discover them through experimentation necessarily. Now, one of the things about a virtually built or a virtual system, it's, sorry, I guess I could try this. Okay, for a virtual system, did my laser pointer? Ah, there it is. I'm so proud of myself. I've never found that before. This is the first time. All right. So one of the great things about, at least a benefit on the virtual system is this: the nominal design and intent is always known. So you can build a distribution around it. When you have a physical system, you get what you get. All right. It's built. It's itself. It's got its own characteristics, and it's not, how can I put it? It's not variable. You don't get a chance to say, well, let's just try I think I'd like to change the center of mass of my vehicle by a couple of, centimeters or something. Or what if I change this bushing or rate of, or stiffness? You start changing those things, on a vehicle, and it gets really expensive and time consuming. But boy, you can do that on the fly if you've got something described virtually. And also get back to, can't use a laser pointer to advance the slides though. I'm learning that quickly. Sometimes, here's the other thing that you learn about these two. Oh yeah, the animation changed too, so you can see the wireframe one is supposed to be the virtual one. So it's in real time or faster. And why that's significant will come up in just a moment. It exists from the very beginning, so you can start learning right away. If you think about a physical system, when does it exist? After you've assembled all of the parts and put it together, right? And when you have a virtual system, if you've got teams of people who are building the individual components, chances are you can assemble and knit them together in a virtual sense very quickly. So they're kind of giving them it's like an anthropomorphism here, but anyway, it says here, despite my transparency, when you think about the virtual system, you don't trust me yet. And that's the thing we've got. We got a trust issue with things that are virtual. We believe things that we see, and we don't trust things that we don't. So it's a paradigm shift in how we think and look at these systems. Somehow we trust physical systems more, even though we may not be able to learn a whole lot from them, okay? The virtual systems can probably teach us a lot more as we exercise them. So moving along. So what's kind of about to be ushered in is kind of like this change in culture. We're going to have to change the way we look at physical tests versus virtual testing. And one of the things that we have to change in the whole culture is this concept of correlation. You guys all know what that's like. You said, oh, I know what correlation means, that if I modeled something and I have a physical representation of them, then when those two plots overlay each other, then I know I've got myself a nice correlated, useful model. And you know what experience, our experience has shown us, that's not necessarily true. You may just happen to have a physical representation that happens to lay right on top of your model for the moment, but when you vary a couple of the parameters of that physical system, it may fall apart. It may not even represent reality. So we have to get to a point where first principles rules, where if we have the physics right and we have our energy balances and things like that right, then you're going to be successful. I should have asked you guys a few questions. Now, what's the kind of composition of the class here? I got people from all different majors, all the engineering majors, computer science too, right? Okay, all right, there we go. Computer science. I'm proud in the back. I'm computer science. That's good. And do I have all levels from freshman through? Okay, gosh, that's awesome. All right, so anyway, you might not have seen a whole lot of correlation just yet. It's coming your way, all right? So be prepared as you move forward. But it's a big thing in modeling and simulation to say you've got a correlated model. Because until people say they have correlated models, they don't believe the models, all right? And we're learning that correlation is somewhat relative. And what we have to do is we're taking the leap to understand that you have to trust the physics that you have built into the tool set that you've got, okay? Well, that doesn't mean you don't sanity check your results either, all right? I'm not saying you don't do that. Because I'll tell you something that our company did, and so did many others. We started building respirators back, right after, COVID hit. We started manufacturing, places where we made masks, but you remember there was a huge need for the hospital respirators and some of these other portable kind of respirators. We had some technology, and we managed to, within about 4 weeks, turn some plants around and started building these respirators, and we didn't build any physical parts. And just think about it. A respirator is a critical device, right? It's safety critical, because if respirator doesn't work properly, that which is supposed to be protecting you and I ends up being something that harms us instead. So that was actually, it was one of our first applications of. That's not a first application. It was a very an application of virtualization that I think would resonate with. I was hoping it would resonate with you, but it resonated with our public when we started to share that this is how we're taking on our product development cycle, or becoming a part of our product development cycle. All right, so the good thing about virtualization is this. It allows us to visualize the things that are otherwise unobservable, okay? Because imagine crash testing. What you happen to be seeing right here is kind of like a movie of so it's actually one of those Hummer trucks impinging like a parking post, that is. And what the deformation that you're seeing is the deformation of the battery pack. We're trying to study, because you see, if we run a sled test, and the sled test is like one of these tests where you take a target, and you've probably seen them on television. You see them crash the car into it, and you notice you don't get a whole lot of those in a day, right? Because once you've crashed that vehicle, you take your data from it, you're done. But as you can see here, you could change you could decide, well, let's move that post over by 2 meters. What happens when it's a little closer to the B pillar or some other part of the vehicle? And you get to evaluate that. And the science has come far enough to where this becomes very significant in giving us insight. So what we're having to do, and what industry is having to do now, is to convince our people and convince ourselves that our capability, we have to persuade ourselves that our tools are capable of producing this kind of truth, okay? Producing truth. So I'm going to skip past this. So ultimately, as it says here on the right side, we're trying to make the subjective objective. And one other thing we're trying to add is this, is that variation has to be a part of standard work. We want to look at how things change with temperature and mass and other property changes, because we don't always build everything identical. So virtualization allows us to do massive runs, not just one or two or 3 or 4. We can do hundreds, and we're moving at the speed in which we can put cores into a compute farm so that we can run them. All right. So now, in an industry where you might be limited to how many prototypes you can build, if you can build a virtual one, if you buy the computing space, you might be able to build hundreds of prototypes at one time and test them, and you get the benefit of that. As I was talking before about physical tests versus simulation, this is just an example. It just shows where, this is actually considered fairly well correlated, depending on the dynamics here, but a single physical test in red, and then this is a virtual simulation of that same scenario. The only thing about the physical system is you don't get this family here where all of a sudden we turn on all of you do a DOE study, for instance. That means we vary the parameters of the system and see, hey, where does the response go now? Because when we're designing, we have to be able to design for the variation that can just be in the whole manufacturing process, or the variation that can be in from one piece of material to the next. And it has to fit within a band, and that's what you see there. You see kind of like this band of where things can operate. So again, remember this, virtualization and physical test doesn't have to be a direct replication. So I'm going to skip through the rest of this slide to take us to here. Our leaders, or we need leadership to get us past some of these fears that are going to allow us to take these next steps. And that's where I wanted to kind of take the rest of our discussion, because there's a lot of issues with risk, and managing risk is one of the central things that leaders have to do. And getting comfortable. And remember to do this, question everything, as Einstein would say. And there's a couple other concepts that are out there that we've been exploring, something called, I'll go back one, fungibility. And that's where we as individuals, if we have the right tools, we can do many types of jobs. It's almost like you can be placed in various types of operations and you can do very well there. So fungibility is kind of like, it's like being an athlete. It probably says, hey, I can do many things. I can jump, I can run, I can sprint. It's being very athletic in the way in which you can function and work, and kind of understanding how all these tools come together when it comes to virtualization. A person who's kind of has that training and background allows them to be fungible. It's anybody want to? That's a buzzword for the day, so to speak. So think about fungible, because you're going to keep hearing that in literature and in lectures.